Yeah, okay. Uh, Hello, everyone. Welcome back to this week's QFTMS seminar. And today we have Ivano Basile. He's going to talk about non-supersymmetric branes and discrete theta terms. Thank you for accepting our invitation. And it's floor is yours.
All right, thanks a lot. Thank you for the kind invitation. And yeah, I'm very happy to participate in this super nice series that you're organizing. I think it's a really great initiative. And in the spirit of the initiative, I just want to start by saying, please interrupt me at any moment. Even though I cannot see your faces, I'm happy to discuss and stop talking at any moment if you have any questions. All right, so the topic is something with my colleague Vittorio Larotonda. And this paper was essentially a follow-up of another paper written by Tachikawa and Zhang in 2024. So these are basically the two papers that I'm going to talk about. I'm going to talk about the method that the authors of the first paper used and the method that we used and how they compare. In the general context of these discrete topological terms or discrete theta angles in non-supersymmetric string theory. All right, so what's the big idea here? What's the big picture? Well, the big picture is exploring what string theory is, right? And by that, I mean really some non-perturbative aspects of string theory, because we have a very good definition of what perturbative string theory is. And some special cases of this definition, perhaps the simplest cases of this definition, include basically all the nodes of this diagram, right? So this diagram includes, the famous five 10-dimensional supersymmetric strings, type 2A, type 2B, type 1, and the two supersymmetric heterotic strings. Then this hexagon also includes, for completeness, the low energy limit of 11-dimensional M theory, which is 11 dimensionals per gravity, which is not quite perturbative string theory, but it's still something that we can understand quantitatively in some limit. Now, this is the whole diagram of 10-dimensional perturbative string theory plus 11 d per gravity, as far as tachyons are absent, right? So there are a few more nodes in this diagram if you accept that that the others have tachyons in 10 dimensions, and then who knows what the fate of these tachyonic configurations are. So insofar as we restrict to 10-dimensional settings without tachyons, which are perhaps the simplest ones that we can think about in perturbative string theory, this is the diagram, right? Now, what we would like to understand in this diagram is more than just the vertices themselves, which characterize perturbative limits, but also the connections between these vertices, which denote string dualities, right? So T duality, S duality, and other operations that connect these perturbative limits are perhaps the deepest and richest aspect of what makes string theory, so compelling as a UV complete candidate for quantum gravity. And in order to understand these dualities, it's important to understand non-perturbative aspects of this diagram, right? It's important to understand non-perturbative is absent, right? Because of course supersymmetry gives us a lot of control over these dualities, and we would like to say something without using it. And in particular, beyond these five supersymmetric cases, plus 11 dimensional superiority, there are three options that have no tachyons. So, by the way, just for completeness, these type 0A and type 0B corners do have tachyons, but I put them in the diagram in order to see how to get to this 0 prime b vertex, which does not have tachyons. Now, this is relevant for us because the case that I'm going to be interested in this talk is this particular corner, which people denote as SO16 times SO16. What this means is that this describes a perturbative string limit of the heterotic type with a gauge algebra, which is that of SO16 times SO16, right? Now, this particular, let me call it heterotic theory, even though one expects all of these to be connected into the same unique theory. This heterotic theory has been studied since the 80s, and several aspects of it are decently understood, at least in perturbation theory. The idea of this talk is to study a particular term in the effective action of this heterotic theory that is completely invisible in perturbation theory, right? So the hope is to get to understand some non-perturbative aspects of non-supersymmetric strings, such as this particular case, by studying a piece of the effective action of these theories that perturbation theory can never see, right? So what does this theory look like? Well, as far as the perturbative slash local part, the part of the theory that we can describe with a local effective action, it pretty much looks like our garden variety low energy effective action for string theory. It includes gravity, of course, right? So it lives in 10 dimensions because that's what we chose to study. And because it's a heterotic string, not only it includes gravity, it includes also the dilaton, this real scalar field that controls the string coupling. It includes this B field, this local two-form field whose curvature H controls the kinetic term. And it includes Yang-Mills fields, whose gauge algebra is this SO16 algebra, right? Now, the global form of the gauge group is more complicated than that, but again, it does not concern us for this talk. Now, beyond bosons, this theory, it also includes fermions, and this is actually necessary because it does not have tachyons. It turns out that there is a deep relationship from the worldsheet point of view between the absence of spacetime tachyons and the presence of spacetime fermions. Now, there are fermions, and they are, in fact, chiral. This is a chiral gauge theory. Yet, there is no gravitino in the spectrum. This reflects the fact that this theory is just plain non-supersymmetric. Right? Now, a particularly impactful manifestation of the absence of SUSY in spacetime is that loop effects generate a vacuum energy. They generate a potential for the dilaton. And in particular, in 10-dimensional Einstein frame, it looks like this particular exponential here to one loop order. And the presence of this non-zero potential complicates things considerably, right? So in particular, there is no 10-dimensional maximally symmetric solution to this effective field theory. The best we can do is to look for vacua of the Freund-Rubin type, something like anti-de Sitter times some space, right? Compact symmetric space, and other more complicated ones.
I think your internet connection is a bit unstable. Sometimes your voice is we cannot hear you, so I don't know. There is something you can do, but
so I could, in principle, remove the Wi-Fi of the institute and connect to my phone's network. If you think, I think this could be more effective. Do you want to try?
Yeah. Go ahead. Let's try, and if it's not
right.
good enough, you can switch back to the institute.
All right. I apologize for the inconvenience.
No problem. It happens like every now and then, but then sometimes it can affect the presentation. So.
Hello? Am I still in the call?
Yeah, you're still in the call, yeah.
All right. And is the screen still shared?
Yeah, everything's fine. Yeah.
Perfect. Okay, so now I switched connections and I should be able to keep going. All right. So as I was saying, ironically, I was talking about stability of the vacuum. I was talking about the fact that in the presence of this potential, due to the absence of supersymmetry, the structure of the vacuum is much more complicated than usual, right? In particular, we have been able to construct vacua that are weakly coupled, weakly curved, and we believe that they are long-lived, or at least as long-lived as it gets, but never fully stable, right? So given these complications that already arise at the level of the two-derivative local low-energy effective action, how could we possibly hope to make progress in the quest to understand non-perturbative aspects of this theory, right? It seems hopeless. Now, of course, in general, the first crutch that people use all the time in order to investigate non-perturbative aspects of physical systems, strongly coupled physical systems in particular, is of course supersymmetry itself, which helps with the dynamics. It protects quantities from receiving corrections due to the dynamics and so on. And as I just said, we don't have this crutch, so we cannot use it. The only other option, besides divine intervention, I suppose, is topology, in the sense that we can look for pieces of this theory, in particular terms in this effective action, which are topological invariants of some sort. Something that is essentially, it depends very little on the specific dynamics, whether weakly or strongly coupled, and we can hope to compute these quantities exactly because they are robust against any sort of continuous deformation, right? Even without supersymmetry to help us. And there is a particular kind of topological term that we focus on, and it's a type of theta term, right? So a theta term is just some essentially, well, I will describe now what I mean, but in this specific case, but the simplest example perhaps that people are familiar with is the theta term of electrodynamics, or QCD, right? Which is the F wedge F kind of term in 4 dimensions, right? And usually it's a term in the effective action which is the integral of over space-time of a characteristic class. A characteristic class either of the tangent bundle of space-time or of the principal gauge bundle, or both. Now, in this case, we are going to talk about a gravitational theta term, so something that has nothing to do with the Young-Mills gauge sector of the degrees of freedom at play. So it only depends on the gravitational sector. And moreover, it's a discrete kind of theta term, right? It's a discrete theta term, meaning that it cannot be written as the integral of some differential form, right? Sometimes characteristic classes can be represented by differential forms in cohomology. This is the content of the Chern-Weil correspondence. But when it comes to discrete theta terms are associated to torsional cohomology classes, which means that they cannot be written as the integral of a local quantity. Nevertheless, they are part of the effective action, in the sense that if we think of the effective action as some map that maps space-time manifolds into phases, right, which are the phases that enter the functional integral of the effective field theory, then the meaning of a theta term is well defined. It just means that it's a piece of this effective action which is invariant under cobordisms, right? This is what we mean here by a gravitational theta term. It only involves the space-time manifold and no data of gauge bundles and so on. Now, because this kind of theta term is invariant under cobordism by definition, we can consider manifolds that detect this theta term, meaning generators of the Bordism group, right? And what is the Bordism group in question? Well, even if we remove the gauge part of the degrees of freedom of the theory, the heterotic theory contains, beyond gravity, contains this B field, right? And the B field must satisfy a particular Bianchi identity that is not just that its curvature is closed, as is usually the case, but rather the full gauge invariant curvature treeform H is not just dB, right, as would usually be, but it's dB plus something else. And this combination H, this sort of gauge invariant field strength, is not closed anymore. It satisfies dH equals P1 halves, where P1 halves is really a shorthand for a particular canonically defined characteristic class on spin manifolds, who twice of which is the first Pontryagin class of the tangent bundle. So this is called the anomalous Bianchi identity of heterotic strings, and it comes from the consistency of the worldsheet description of heterotic strings propagating on spacetime, among other ways of deriving this identity. And because of this reason, like manifolds equipped with such a B field satisfying such a Bianchi identity are called string manifolds. So these are spin manifolds equipped on top of the spin structure. We are equipping the manifold with a B field that satisfies this identity, right? This is what a string manifold is for us. And this is part of the topological data that describes space-time, which means that when we look for possible candidate theta terms in the effective action as Bordism invariants, we need to look at Bordism groups of string manifolds. In this case, 10-dimensional string manifolds, because we are, our space-time is 10-dimensional. Now, it turns out that the group in question is non-trivial, right? It contains a Z2 factor and a Z3 factor. And for reasons that I will get to at the end of the talk, so stay tuned, we only care about the Z3 factor. So let's say, regardless of this distinction, this group is generated by exotic spheres, 10-dimensional exotic spheres. And these are very complicated manifolds. But if we only focus on the Z3 part, a generator of the Z3 subgroup is represented by a particular simple exotic sphere, which is just a group manifold, the group manifold of SP2. So this is a 10-dimensional manifold of symplectic unitary matrices, let's say 4x4 unitary symplectic matrices. And this particular group manifold is very convenient for us, as we will see later, as a probe for this topological term. So in other words, our topological term is just the phase that the effective action assigns to SP2, right? This is our definition, working definition of this gravitational theta term. Again, if you have any questions, please interrupt me at any moment, because I cannot see your expressions to see if I'm being clear or not. All right. So here, let me give you just a punchline, so you can decouple if you're not interested anymore. So this is the punchline of these two papers: the first one written by Tachikawa and Zhang, and the follow-up written by myself and Vittorio. The punchline is that this particular theta term is not zero, right? Turns out it is, again, as we know, it's a Z3 valued topological term, which means that as a phase, it's a multiple of 1/3, modulo 1. And therefore, it can only be 0 or plus or minus 1/3, up to modulo 1. It turns out that it is not 0. This, I think, we established fully. What we cannot seem to establish is the sign. We cannot establish whether it's plus or minus 1/3, in the sense that these two papers got the two possible opposite results, even using apparently the same conventions. So what we differed by in approach was that the way that we computed this topological term using anomaly inflow of some kind that I will get to, used a slightly different procedure, right? So it is possible that the discrepancy can be accounted for by understanding this difference in method and the physics that is captured by the different anomalies that we used to compute this theta term. So this is sort of an open question for us: which one is the correct sign? Whether both signs are realizable? But nevertheless, we can say that this term is not zero, at least. All right, so let's see how to get to where we want to get. So as I mentioned, this theta term is connected to anomalies and anomaly inflow of some kind. How does it work? Well, it's sort of a discrete counterpart to something we already know. Something we already know, which is a continuous topological term in the effective action of heterotic strings. And this continuous topological term, which means that it can be written as the integral of a local quantity, is just the famous Green-Schwarz term that is crucial for anomaly cancellation, right? So the goal is to understand how the Green-Schwarz, the continuous piece of the Green-Schwarz term, contains a discrete refinement, so to speak. And the way that we work out what this discrete counterpart to the Green-Schwarz term is using the existence of 5 branes, right? Heterotic 5 branes. And the connection is that the Green-Schwarz term in the 10-dimensional effective action is related to the anomaly of these heterotic 5 branes. And in particular, it's related to the local part, the perturbative part of the 5-brane anomaly. But as we now know, we have known for several decades, perturbative anomalies are not the full story, right? There are also non-perturbative discrete, or if you will, global anomalies that cannot be described perturbatively. And by analogy, we work out what the discrete part of the Green-Schwarz term, this discrete theta term, would be in order to implement the correct anomaly inflow between 5 branes and the 10-dimensional spacetime theory at the level of non-perturbative global anomalies. Right? This is sort of the roadmap. All right, so if there are no questions about the general plan, I will start describing anomaly cancellation in string theory. All right. So how does the general story work? So the general story, again, as anticipated, has to do with this celebrated Green-Schwarz mechanism. Perhaps the complete name should be Green-Schwarz-Sagnotti-West mechanism. And this mechanism has to do with the anomaly polynomial that describes perturbative anomalies of field theories. And the idea is that sometimes the anomaly polynomial of our theory is just plain zero. There is no anomaly to cancel. And this is the case, for example, for type 2a and type 2b strings. Right? In the case, instead of like heterotic and type 1 strings, even in the supersymmetry case, the anomaly polynomial does not vanish, in fact, but it does factorize. Right? It factorizes into a product of lower degree characteristic classes or polynomials. And one of the two factors of degree 4, this 4 form x4, just so happens to be precisely the right-hand side of this anomalous Bianchi identity of the B field. Right? Now, because of the structure, it turns out that it is possible that the effective action contains an additional term, this Green-Schwarz term, that mixes the other piece of the anomaly polynomial, x8, and the B field together. It's B2 wedge x8, in such a way that the total anomaly of the theory, combining the anomaly polynomial coming from the chiral degrees of freedom and the classical gauge variation of this Green-Schwarz term, then total anomaly will vanish, right? So this is just a mere possibility at the level of effective field theory, but it turns out to be absolutely necessary at the level of the full string theory. In other words, from string theory, we don't get to choose whether the Green-Schwarz term is there or not. It's either there or it's not. And people computed it, and they showed that it is in fact there, it has the right coefficient, and the full anomaly cancels. Right? So this is the punchline of the first superstring revolution of 1984 that led to a considerable spur of interest into the field. Now, this story, this is a perturbative story that generalizes to non-supersymmetric strings as well. So all the models that I showed you, and in fact, all of them, period, share the same features. So either the anomaly polynomial just vanishes, or it factorizes in such a way that the Green-Schwarz mechanism takes place, perhaps not just via the B field only, but multiple forms of different degrees can come into play. Right? Now, in the heterotic case, it is just the B field that does the job, so it's a standard type of Green-Schwarz mechanism, and that's it. So the perturbative anomalies vanish. Now, as I said before, of course, we know that there are global anomalies, meaning gauge anomalies that cannot be captured by perturbation theory. And already many people, decades ago, including Witten, showed that these kinds of global anomalies vanish for supersymmetric strings. And then, even further down the road, around maybe 2018, we fully established that the most general kind of non-perturbative anomaly, the so-called Diefried kind of anomalies, are captured by even more refined topological invariants, namely Bordism invariants and eta invariants in particular. And these fully general kind of global anomaly was also shown to vanish in some supersymmetric settings. And finally, with my collaborators Aaron De Bray, Matilda Delgado, and Miguel Montero, a few years ago, we showed that these anomalies also cancel in the non-SUSY cases, up to a few asterisks in one particular case, this 0'B case. But let's say it is almost entirely established that all of these anomalies, global or local, cancel always with and without spacetime supersymmetry, right? So the 10-dimensional physics is safe, is what I'm trying to say. Now, one byproduct of our analysis in the case of the non-supersymmetric heterotic theory that I described earlier is that we got out of anomaly cancellation a proposal, a natural guess for the chiral degrees of freedom that live on the heterotic fibrine. Right, so we know that the heterotic fibrine exists in the non-perturbative spectrum of heterotic strings, but in the non-supersymmetric case, because we don't have access to reliable dualities, we cannot really tell what that brane is, what the degrees of freedom on it are. We just know that the chiral sector of these degrees of freedom has to satisfy anomaly cancellation, in the sense that even if the 10-dimensional theory is anomaly-free, once we insert a brane in space-time, then there is a new anomaly that arises from the presence of this brane. And then the degrees of freedom on the brane have to cancel it, right? So this is anomaly inflow, in this case of the heterotic fibrine, and we can use it in principle to fix some properties of these chiral degrees of freedom on the fibranes. Now, in the case of the non-supersymmetric heterotic string, again, because we don't have access to a dual weakly coupled description, we don't have a microscopic handle on these heterotic fibranes. What we do have is a handle on the gauge soliton that is produced if you put fibranes in space-time. So because fibranes are charged and they're heavy, they curve space-time and gauge fields alike, and they produce soliton. And this soliton, it's a solution of the of the low energy effective field equations, and we can study its zero modes to understand what kind of chiral degrees of freedom it can host, and we can use anomaly inflow to fix some of their properties. Now, a crucial property that anomaly inflow has to satisfy is that the anomaly polynomial produced by the degrees of freedom of the fibrane should contain this X8 piece, right? This X8 that appears in the Green-Schwarz factorization. This is absolutely crucial, but it does not have to be exactly that. It can be that plus other pieces, and these pieces should factorize on their own. And factorization of these other pieces can be cancelled by another Green-Schwarz mechanism, this time not in space-time, but on the brane itself, right? This is what leads to a consistent chain of anomaly inflows that cancels all of the anomalies. Now, the upshot of this analysis is a proposal for the spectrum, the chiral sector of the spectrum of the fibrane. And this is by no means the only possibility, right? So in particular, there was a much older paper that gave another proposal. And so the spirit of our work here is to test the validity of this proposal by computing this topological term using the spectrum according to the roadmap that I showed before, and see whether the final result agrees with some other method of calculation. And if not, that's, we should try to understand why. All right, so how do we start connecting the anomalies on the fibranes to these topological terms in space-time, right? On one hand, we have a 6-dimensional theory that lives on the world volume of these heterotic fibranes. On the other hand, we have a 10-dimensional theory, which is just this heterotic string, right? How do we connect these two? Well, one way to do it is to realize that we can, if you put a fibrane in 10-dimensional space-time, it has 4 transverse directions. And these 4 transverse directions assemble into the angular part, which is a 3-sphere, and then the radial part. Now, there is a way to rearrange this structure by thinking of 10-dimensional space-time as the total space of a fibration that includes the angular 3-sphere and then this world volume including the radial direction. This is useful because fibranes are charged under the B field, right? That's sort of the definitional feature of these fibranes. They are magnetically charged under the B field, and therefore this charge is radiated as a flux, as the flux of this B field, which is a 3-form field strength, and this flux threads the angular sphere. This is exactly the same as what happens if you put an electron in space and then you surround it by a sphere and you use Gauss's law, right? So there is flux.
For every 10D manifold, we can do this. So is that true? Or
well, I would say for any consistent background of the heterotic string.
Okay.
Now, in the at the level of detail that we're studying things in, we don't really care whether this manifold solves, or rather whether the fields on this manifold, the metric, gauge fields, and so on, solve the field equations. We do not care about that. And the reason is that the expectation is that the quantities that we are computing here, anomalies basically, do not really care whether the metric and gauge fields and so on solve the field equations, because they do not depend on metrics and gauge fields. They only depend on the tangent bundle and principal gauge bundle and so on. They only depend on topological data, is the idea. So in principle, yes, we should look only at manifolds that solve the field equations and so on, but we expect that the results of this analysis do not depend on that. But as long as these backgrounds are consistent, we can put fibranes in them. Now, if the fibranes are placed on a compact space, then it's not as easy. You have to satisfy tadpole conditions, right? You have to make sure that the total charge on the compact space vanishes, but in this case, we're not doing that. All right, thanks for the question. So let's say you should picture M10 as just our group manifold SP2, basically. This is the manifold that will detect the discrete theta term in the end. But for thinking about the general picture, think Euclidean space, and you just place a 5-brane in Euclidean space. You can think of that. So yeah, the point is that this S3 is the part that is threaded by the flux that is radiated by the 5-brane. And the rest is basically the world volume of the 5-brane plus the radial direction away from it. And this construction of this world volume as the boundary of a 7-dimensional manifold that extends away from it is precisely the construction of the anomaly topological field theory, right? This is the kind of construction of a 7-dimensional manifold that hosts the anomaly of the 6-dimensional world volume. So this is the connection, at least here at the topological level, between the anomaly on the 5-brane world volume, which is described by a 7-dimensional topological field theory, and 10-dimensional space-time, which is the thing where that detects the topological term of the 10-dimensional effective action. This is the connection. In particular, because as I said before, we want to detect the theta term using the generator of 10-dimensional string Bourdism as SP2, the SP2 group manifold. There is a very nice fibration precisely of this type, which involves just spheres. It's a kind of Hopf fibration, if you will. So the fiber is S3 and the base is S7. So this is the connection that we're going to look at. So we want to relate the anomaly of the 5-brane theory on the 7 sphere, which is a kind of Witten anomaly, to the discrete topological term in spacetime. Now, what kind of anomaly are we talking about? Anomaly under what? Under what group? Well, it cannot be any gauge groups because we just said that it's a purely gravitational theta term. So it has to be an anomaly that involves somehow the tangent bundle of spacetime. And in particular, it turns out that it's enough to consider a very simple SU2 group here. Namely, the SU2 rotations of the transverse directions of this, let's say, the SU2 that acts on the sphere. And you can think of it as the piece of the space-time tangent bundle that consists of the normal bundle to the world volume of the 5-brane, right? And it's a subgroup of that, of course, because the normal bundle is an SO4 vector bundle, right? So this locally we decompose the SO4 Lie algebra in 2 copies of SU2, and we pick one of these SU2s. Now, in the supersymmetric setups, this SU2 is the R symmetry of the world volume theory of the 5-branes. Now, here we are in a non-supersymmetric context, so there is no such interpretation. This is not an R symmetry. Still, it's just some SU2 normal rotation acting on the world volume, okay? So we consider anomalies of the 6-dimensional heterotic 5-brane theory under these normal rotations. And again, these anomalies are captured by a 7-dimensional topological theory. And it's enough for us to consider this 7-dimensional topological theory on the 7th sphere, because already on this very simple manifold, this SU2 anomaly can be detected. In particular, it is detected by the fact that there is on this S7, there are non-trivial SU2 bundles that are classified by this modulo 12 homotopy group, right? This is the standard way that Witten taught us how to study global anomalies, even though this is not the most general anomaly a priori. But it is enough to detect the topological term in 10 dimensions. So this is the idea, okay? Now, again, the recap is that we want to compute or study this Z3 valued topological term. And this is going to be the phase of this 10-dimensional partition function or effective action evaluated on this generator manifold SP2. And we turn off all the gauge fields in such a way that this X8 polynomial, so the continuous part of the anomaly, if you will, or the Green-Schwarz term in 10 dimensions, is just 0. So in this non-supersymmetric heterotic string, this is the case. And this is why we get to study the discrete part, because the continuous part is 0. So there's a clean separation between the continuous part and discrete part. In the supersymmetric heterotic strings, this is not true. All right, so how do we study the global anomaly on the 5-brane, and in particular the resulting anomaly inflow that gives us the 10-dimensional discrete version of the Green-Schwarz term? Well, we do it by converting the global anomaly under this SU2 normal group into a local anomaly under a bigger group. Right? This is a standard technique to evaluate global anomalies, which is to say that if your spectrum under your gauge group G can be thought of as a branching of a spectrum and of representations of a bigger group, right? And it just so happens that that bigger group has no global anomalies, only local anomalies, then the global anomaly under the smaller group can be computed as a local anomaly under the bigger group, right? This is a standard procedure. And in particular, in this case, funnily enough, we can choose this bigger group of SU2 to be SP2. Now, this is the SP2 thought of as an auxiliary gauge group to compute the global anomaly, whereas previously we were talking about SP2 as the 10-dimensional space-time manifold, right? So these are two appearances of SP2 in this work, but let's not confuse them. So we are eventually going to look at the 10-dimensional theta term in SP2 space-time, but here from now on we use SP2 as this auxiliary bigger gauge group that we use to compute the SU2 anomaly. Okay.
Can you repeat again what was the relation between like this bigger group and the smaller group? I missed
Right.
it.
So in general, the idea is we have some gauge theory, some gauge group G, some chiral matter that with some representations of G. And we want to compute a global anomaly, right? Suppose that there are no local anomalies, we want to compute a global anomaly. Usually this is pretty hard, right? On a general background, it's hard to compute these anomalies. And this strategy is to say, hey, suppose that our spectrum of G representations can be thought of as H representations, where H is a bigger group, as in G is a normal subgroup of H, right? So if you can write down some H representations that branch into G representations under the inclusion of G into H, right? Then you can think of the G anomaly as an H anomaly under this bigger group. Now, the advantage of doing this is that there are sometimes choices of embeddings G into H such that H only has local anomalies, no global anomalies, right? So we can turn a global anomaly, a global G anomaly, into a local H anomaly. This is the strategy. And local anomalies are much, much, much easier to compute. That's the idea.
Okay, I see.
Right. Very good. So this is the Elitzur-Nair method, if you want to look up some literature. And in this particular case, there's an obvious choice of this supergroup, let's say, so this bigger group of SU2, because SU2 is just SP1, right? And there's an obvious embedding of SP1 into SP2. Just by block diagonal embedding of the matrices. And the possible ways of basically extending this non-trivial SU2 bundles on the 7th sphere into the interior of a seventh sphere, which is an 8-dimensional disk, are classified by this exact sequence. This is the homotopy fiber sequence associated to the fibration of sp2 with the three-sphere fiber. Right? So there is this long exact sequence of homotopy groups, and for us, the interpretation of it is that, again, we have a potential global anomaly on the six-dimensional theory that is classified by this Z12, which means that there is a non-trivial SU2 bundle on the seventh sphere. And therefore, we cannot just compute this anomaly as a local anomaly just by saying, oh, the seventh sphere is the boundary of an eight-dimensional disk. And then the eight-dimensional disk hosts an anomaly polynomial, right, in A of dimension of order 8, and that's it. We cannot do that, right, because these global anomalies are not reducible to local anomalies under SU2, but they are under SP2, right? And the way of extending this now SP2 bundle into the disk can be classified by this homotopy fiber sequence. And what we care about is then writing this SU2 global anomaly as a local anomaly. So the integral of an anomaly polynomial of sp2 degrees of freedom integrated over the disk, whose boundary is the seventh sphere that hosts the anomaly topological field theory of the fiber. Now, this anomaly polynomial will also include another piece, which is this world volume Green-Schwarz term that I alluded to before, which is necessary to cancel all the anomalies of the 10-dimensional space-time coupled to the 5-brane world volume. So we know what this term looks like. It was derived long ago in several papers. And now our job is to understand this new piece, like how to translate the global SU2 anomaly, which is just an eta invariant of the gauge bundle on the seventh sphere, as an anomaly polynomial of sp2 fermions now, right? So how to do this? Well, the way that Tachikawa and Zhang did it, and we just repeated their derivation in a slightly different context, was to use this exact sequence. Now, this exact sequence contains these maps, and these maps are multiplication by 12 and reduction modulo 12. In particular, if you follow what this guy, this Z group does, where this goes, it just goes to 0, right? Because, of course, if you follow two arrows in an exact sequence, you end up to 0. This means that you can think of as this guy ending in, not into the homotopy class that represents the non-trivial bundle that we wanted, but in 12 times that, which is just 0. It's a trivial SU2 bundle, right? And we can exploit this, and we can exploit the fact that anomalies are homomorphisms. So they behave additively. The phase is additive under the addition in homotopy, and we can use this to say that if we want to compute the anomaly of our generator of our homotopy group, namely the non-trivial, the most non-trivial SU2 bundle on the seventh sphere, but instead of computing that, we compute 12 times that, and then we divide by 12, right? Because we only care about the result modulo 1 in any case. So we compute 12 times the anomaly of the generator, which, again, because anomalies are homomorphisms, is just the anomaly of 12 times this generator, which in homotopy means the trivial bundle, right? And this is the image of the generator of this homotopy group, which, because this corresponds to SU2 bundles on the seventh sphere. This corresponds to sp2 bundle on the eighth sphere, right? And we're getting closer to a local anomaly of sp2. So this means that we can write this guy as the integral over the disk of some anomaly polynomial. And the only thing that matters is that the sp2 representations that we choose for our fermions reduce to the SU2 representations of the actual fermions on the fibrane, right? This is our constraint. And the result does not depend on how we choose to lift SU2 representations to SP2 representations. This is, because in the end we're computing SU2 anomalies. This SP2 bigger group is just an auxiliary tool, right? So we can write the anomaly in this way, but this is pretty awkward because we are integrating an anomaly polynomial, which we're going to compute in a moment, over a disk. And this is because we extended the 7th sphere into an 8th disk. And this disk still has a boundary. But now, because this 12 times the generator of this homotopy group corresponds to a trivial bundle, or a bundle that is homotopically trivial, it means that we can glue to this disk another disk where we just extend the SU2 bundle on the 7th sphere trivially as an SU2 bundle inside, because now we are working with 12 times the non-trivial bundle, which is trivial in homotopy. So now we have two disks, one of which hosts an sp2 bundle with a local anomaly polynomial, and the other one which hosts just the trivial SU2 bundle. And now we glue them together, and we get an integral over the 8th sphere, not the 8th disk, the 8th sphere of this anomaly polynomial here, with the understanding that it's only supported on 1/2, right? But it doesn't matter, because out of all the pieces on this in this anomaly polynomial, because this is the integral of our characteristic class on the sphere, the only contribution comes from the highest piece that comes from this trace f to the 4 term that in SU2 would vanish, but in SP2 does not vanish. And the result is this number t, which is whatever coefficient was in the anomaly polynomial. Okay? So this is the name of the game. The name of the game is we take these SU2 fermions or SU2 chiral degrees of freedom on the fibrane, we lift them to SP2 representations in whatever way, doesn't matter how. And then we look at the anomaly polynomial under SP2. This is the local SP2 anomaly. And in particular, we look at the coefficient of the trace F4 term. And that divided by 12 is our theta term, right? This is the procedure. So it's a very straightforward procedure, except for the fact that we need to determine these SP2 representations. And to do that, we need to know what is the SU2 representation content of our fibrane. Any questions? All right, so remember that we had this proposal here. So this is the starting point for us, and then I will describe what Tachikawa and Zhang did and how the results differ. But so for us, this is the spectrum of chiral degrees of freedom on the fibrane. So it involves a bunch of fermions that transform under the spacetime gauge group as this is SO16 and SO16, right? So this is the fundamental of one and the fundamental of the other, or the vector representation of each. And then there are 4 singlets with the opposite chirality. This is what this minus denotes. And finally, in the spectrum, we propose that there is a self-dual two-form field that is not charged under the gauge group. So we take this spectrum, right? And the anomaly polynomial that comes with this spectrum is just the sum of the anomaly polynomials. But this anomaly polynomial, as I said before, is not the full anomaly that contributes to the anomaly inflow between spacetime and the world volume. There are additional pieces that have to do with the fact that, again, there is a Green-Schwarz mechanism on the world volume, so it involves a factorized pieces, which has this Z4 form piece that we know. It's completely fixed. And then, remember, because we determine the spectrum not with a microscopic description, but with the fat gauge soliton that we cannot resolve microscopically, there are additional pieces that involve Yang-Mills characteristic classes, so Chern classes of the gauge group that eventually we want to turn off. So this is the general structure that we need to match. Now, this structure does not have any information about the SU2 rotation group. So what we do is we make an ansatz of the SU2 representation content. So we split these representations into further refinements. We add the SU2 quantum number, right? And we put some unknown constants here. And then we impose that this structure matches the one below. And then we find that the unique result is this. So if I'm precisely one anti-self-dual two form, and we find these two fundamental, these two SU2 doublets, and these SU2 doublets come from these singlets. So these four singlets under the gauge group split into two SU2 doublets. That is the upshot. Right? Now with this content, we can compute this theta term. And this is how we do it. We just say, hey, okay, let's lift the spectrum to SP2. Now, SP2 lifts the fundamental and trivial and adjoint representations of SU2 into its own fundamental and adjoint, right? Which have dimension 4 and 10. And it just turns out that if you compute the anomaly polynomial of such and such SP2 fermions, the coefficient of trace f to the 4 looks like this. And modulo 12, because we have to divide by 12 and take modulo 1, the result does not depend on the adjoint part. It only depends on the number of fundamentals, which branches into SU2 fundamentals and trivials in this way. So this is the value of T. And we know what these guys are. We just computed them before. So the end result is that T is 4 modulo 12, right? And now we can compare a result of T equals 4, which means that theta is 1/3 modulo 1, to what Tachikawa and Zhang did. Now, the difference, as far as no mistakes were made, which we were trying to be careful about, is that the anomaly, the origin of the anomaly is different on the heterotic fiber. So for us, the anomaly came from the chiral degrees of freedom that we guessed directly from the non-supersymmetric theory. We took the non-SUSY theory, we considered the gauge soliton, looked at the zero modes and said, oh, okay, this is a possible natural-looking chiral spectrum. And this is what the anomaly is. Instead, Tachikawa and Zhang computed the anomaly of the non-SUSY heterotic fibrane by taking a difference of the anomalies in the supersymmetric cases, the SO32 and the E8 times E8, right? And this is because formally, the anomaly polynomials of the 10-dimensional theories are related in this way. If you take the SO32 minus the 8 times the 8, you get the one of the SO16 when you restrict to the common SO16 subalgebra. Right? So there is a way to subtract the anomalies of the SUSY theories to get the anomaly of the non-SUSY theory. And in particular, one of these pieces of the anomaly was computed, again, via anomaly inflow, but another anomaly inflow from an 11-dimensional M theory, right? So there are a bunch of pieces that should be tracked that are the difference between the chiral anomaly polynomial of chiral fermions and the anomaly inflow, which can contain additional pieces, right? So we believe that the difference in result, because what they get is the opposite as us, can be due to the fact that we're computing different anomalies, right? The anomalies that they compute have other pieces that ours don't have, or vice versa. Right? So we don't really know the final answer, and we hope to find out eventually. But at least I think we can say with confidence that the theta term is not zero, unless there is another procedure with an additional piece in the anomaly that happens to give zero, but we will see about that. Anyway, just
can I ask
yes.
For
Yeah, of course.
example, like you guessed this like chiral spectrum and computed using that. But okay, so can you confidently say that this guess is correct, or is like because it's kind of natural, right? This guess, but
Right. So yeah, I think we cannot say more than that for now until we have an independent way of checking. And an independent way of checking usually means that we have a dual description where we have access to the microscopic spectrum of the fibrane, which in the SUSY cases is available. They are, for example, the SO32 heterotic fibrane is just dual to a D5 brane of type 1 string theory, which is well understood perturbatively. But we have no way of doing that. So until we do, I don't know how to double check this result.
okay, thanks.
Or maybe we can find yet another method that we're not aware of. All right. Yeah. So finally, I wanted to address why we looked at this Z3 subgroup, right, instead of the full Z6. So the reason is that somehow it looks like this discrete theta term does not know about the Z2 at all, right? Why is that the case? Well, the reason is that if we go a little bit deeper, we can refine our understanding of the theta term, of this particular one. So again, this theta term is a thing that associates to a manifold a phase, right? This is just the EFT understanding. But the question is, what happens if we include the information that this is not just any EFT, this is the EFT that describes the low energy physics of heterotic strings in particular. Well, there is a very well substantiated conjecture, which is this Stolz-Teichner-Segal conjecture, which says that at least at the level of topological quantities, these EFTs that arise from heterotic strings on some background are, let's say, they are classified by some particularly refined cohomology class, which lives in this group called TMF, right? And it stands for topological modular forms. Now, the idea is that heterotic strings, just like any strings, they have the spacetime part of the degrees of freedom that describe strings propagating in spacetime, and then they have an internal sector, right? Now, this internal sector is especially prevalent when we are not in 10 dimensions. When we are below 10 dimensions, there is an internal sector, which may or may not be extra compact dimensions. In heterotic strings, there is an internal sector even in 10 dimensions, right? Because the central charge of this internal CFT, even in 10 dimensions, is 0.16, right? So there is some stuff. There is some CFT in the worldsheet degrees of freedom that does not describe the string propagating in spacetime. They describe some internal part of the string, and in particular, it gives rise to the gauge groups, right, in the heterotic string. Now, these internal conformal field theory part of the worldsheet can be very complicated and abstract to describe, but this conjecture tells us that up to continuous deformations of a specific kind, so sort of the topological data of this internal CFT is a very well understood object in mathematics. It is an element of this TMF group, right, in a specific degree, right? So TMF is a kind of cohomology theory. It's a kind of generalized cohomology theory that has to do with elliptic geometry. It's not quite elliptic homology, but it's closely related to elliptic homology. And, no wonder it describes the topology of heterotic strings, which is sort of governed by how the worldsheet, a worldsheet torus is described by its partition function and so on. So this is the conjecture. And the idea, therefore, is that if this internal TMF class determines the background that gives the low energy EFT data in D dimensions up to 10, then the theta term can be understood as a bilinear pairing between the spacetime manifold, which is a string manifold, and turns out can be thought of also as a TMF class, the spacetime manifold, and the internal CFT data that describes the effective action, right? So there is a bilinear pairing between these two things that is valued in phases. And the idea is then that the topological term should be precisely the image of such a pairing evaluated on generators. And it turns out then that in dimension 10, these groups are Z3, not Z6. So somehow the refinement to understanding the heterotic origin of this theta term somehow seems to know that it's only Z3 valued, it's not Z6 valued. So that's sort of what I wanted to say. Then we extended this idea to other dimensions where these TMF groups contain these distortional subgroups that are non-trivial. And turns out that when it's not Z3, it's Z2. And the only case when this Z2 can be captured by an anomaly of the magnetic branes, like we said before, is only in 8 dimensions. It's the only non-trivial case besides 10. And then we just worked out a formula for the theta term in this case, and we hope to use it for some more general analysis. So this is more or less a summary of what I tried to convey, but I'm certainly open to any questions. So thank you for the nice questions and the attention.
And thank you for this very, I think, pedagogical and explicit talk. And if there are any questions, you can ask. Also, I can turn on the recording if some people don't want their questions to be heard on YouTube. So okay, then now I'm stopping the recording. Maybe some people want to, ask questions of the
record.
Yep.
All right.